Hi guys, in this video we're going to take a look at probability density functions, the normal distribution, properties and notation, finding probabilities for normal distributions, examples, and then we'll finish with a summary.
So what exactly is a probability density function? We have so far been calculating probabilities mostly for discrete distributions. Let's say we are flipping a fair coin 10 times. Then we can model this using a binomial distribution with index 10 and parameter 0.5. Similarly, we could be rolling a single unbiased die. Then the value of the probability that x is equal to little x is 1/6 for all values of x. And in this case, the values of x we can take are x equals 1, 2, 3, all the way up to 6. These are both examples of discrete distributions, the binomial distribution and the discrete uniform distribution. We have seen that probabilities of a continuous distribution can be described by the area under a graph of unit area. So given a graph with x, we can pick, say, two values a and b, and the probability that x is between a and b strictly is the same as the area under this graph. In total, the area under the graph is 1 over its whole domain. The equation of the graph of a continuous variable is called the probability density function. The probability density function for a continuous random variable is the curve representing the probability distribution of the variable. Now we can sketch x against the density function, and at each point here we have the f of x. This is the probability density function, sometimes referred to as PDF, but this can confuse with probability distribution function. Continuous variables found in real life are generally more likely to take on values closer to its average value than more extreme values. In particular, say, the completion time of a race, or the heights of people. We can often model such continuous variables with the normal distribution. So what exactly is the normal distribution, and what are its properties and notation? Many real-world situations can be modelled by the normal distribution. The normal distribution is a continuous distribution that can be used to model many naturally occurring characteristics. There are many examples of continuous variables that can be modelled using the normal distribution. Again, the heights of people in a large population, or the weights of elephants in a savanna, or the time taken to run a marathon by runners, and finally the journey time to school by car. A normal distribution is specified by two parameters, called the mean and the variance. We write the mean as mu and the variance as some number sigma squared. Recall that in general the square root of variance is the standard deviation, and so sigma on its own would be the standard deviation. If a variable x follows this distribution, we can write that capital X is normally distributed, so the little twiddle symbol and then an n, with parameters mu and sigma squared. These are the mean and variance. The normal distribution has a bell-shaped symmetrical curve with asymptotes at each end. In particular, this shape is what we call bell-shaped. We can see that it's symmetrical about this middle. And at these two ends we have asymptotes. Recall that a point of inflection is where the curve changes from concave to convex, or convex to concave. Suppose we have one of the following two graphs. Here we have a convex part of the graph, and here is concave, and similarly concave here, and convex here. We have these points in between, which are called points of inflection, where it changes from one state to the other. A normal distribution has points of inflection at mu plus sigma and mu minus sigma. Again, these are here and here. These again are called points of inflection. This can be used to estimate the standard deviation from the graph of a normal distribution. So it turns out that these points of inflection occur precisely at mu minus sigma and mu plus sigma. It also turns out that the distance between these inflection points and this central line in the middle is also sigma, and therefore we can approximate or estimate the standard deviation from this graph. The mean corresponds to the maximum point on the graph of the probability density function, i.e. the mean, which we write as mu, is precisely the value for which this probability density function is maximum, i.e. up here. The standard deviation affects the width of the curve. The first case corresponds to sigma less than 1, the second case corresponds to sigma being equal to 1, and the third case corresponds to sigma being greater than 1. And the reason why the width of the curve changes is because in all three cases the areas have to be equal under the curve. The area under the curve represents probability, and so the normal distribution always has total area under the curve equal to 1. So how can we find probabilities for the normal distribution? The area under a curve can often be found by integration. Let's say here we have the graph of y equals 2 root x. Then if we wanted to find the area under the graph between some values a and b, then to work out this area, we would usually do an integral, namely the integral between a and b of this 2 root x dx. However, the expression for the normal distribution curve cannot be integrated using methods learnt in integration at A-level. It turns out that in general, the function f of x, which is the probability density function, in general is equal to 1 divided by the square root of 2 pi sigma, and then we have e to the power of minus x minus mu, and then we have it all squared, and then we divide by 2 sigma squared. This is quite a complicated function, but even something as simple as the case when mu equals 0 and sigma equals 1, we have a constant multiple of e to the minus x squared. And this function is not easily integrable. However, we can find the probabilities for a normal distribution using a calculator. Given x, which is normal, with mean mu and variance sigma squared, given the values of mu, sigma, and x, we can calculate probabilities. Calculators have an inbuilt normal cumulative distribution function, which gives approximations to normal cumulative probabilities. We can only find the approximation for the probability of x being less than or equal to a certain value little x. This is because it is based on an integral, and so in general these values are only approximate. It is often useful to sketch a diagram to determine the probability we are trying to find. For example, suppose that x is normal with mean 20 and sigma squared, i.e. the variance, 4, and we want to find the value of the probability of x being between 17 and 21 inclusive of the endpoints. Then we can draw this graph, and we have the mean at 20, and correspondingly we have the endpoints at 17 and 21, and so we're looking for the probability of x being between 17 and 21 inclusive, and looking at this graph we could actually work this out by doing the probability that x is less than or equal to 21. This is all of the area under this graph up to the 21, and then we will subtract the probability that x is less than or equal to 17. This is the area up to the 17, which gives us precisely what we want, the area between 17 and 21. We can use a calculator to calculate these values. Now, the calculator that I use only lets you do the cumulative probabilities in one go. So you can actually find this value straight away with this calculator. Now, your calculator may only allow you to do things like this, and I would definitely get used to, if that's the case, doing things like this, calculating these values individually. To demonstrate how to calculate these values with this calculator, what's going to happen is we're going to have a lower bound list and an upper bound list. Because we have the probability of x being less than or equal to 21, this goes all the way down to, well, minus infinity. So what I'm going to do is to put in a very big number. I'll put in minus 10 to the power of 99. And similarly here for the second one. And then here we have our upper bounds, which are 21 and 17 respectively. And now we go on distribution and then normal, NCD for normal cumulative distribution rather than NPD, which is now normal probability density. And then we have our sigma and mu. I've already put them in here. We have our sigma being 2 because we're given that sigma squared is 4. So sigma is 2. And similarly, mu is 20. By executing, we get our two values, 0.6915 and 0.0668. And so we can write these down and subtract them, and we have the 0.6915, and then we subtract the 0.0668, and this gives us 0.6247 to 4 decimal places. Now again, that was a strange illustration, having to use this minus infinity effectively here and here. But again, this calculator can directly find the value. If I put in for the lower bound 17 and for the upper bound 21, then going into distribution, normal and NCD, everything's still correct. Executing gives me this value straight away. Not all calculators have this function, and so I'm demonstrating how to do it using these kind of probabilities, because that's how your calculator might do it. And it's better for the examiner to see that you understand how to split up this kind of probability into a subtraction. Now notice a difference to discrete random variables. If x is a continuous random variable, then we have that the probability of x being less than, i.e. strictly, little x, is actually the same as the probability that x is less than or equal to little x. This is because if we consider the two separate situations, x being less than x strictly and x being less than or equal to x, then to calculate these probabilities we're looking at the area in this section, and there's no area corresponding to the equality case. So the probability that capital X takes any single value is 0. And therefore, there is no difference between these probabilities. Now for a normally distributed variable, it is the case that approximately 68% of the data occurs within the area plus or minus 1 standard deviation from the mean. Similarly, approximately 95% of all data occurs within 2 standard deviations of the mean. And similarly, approximately 99.7% of all data occurs within 3 standard deviations. Hence, we can assume that a negligible amount of data lies outside 3 standard deviations of the mean. If we look at our mean mu, and we look at the area beyond mu plus 3 sigma and under mu minus 3 sigma, then we can conclude that the probability that x is less than mu minus 3 sigma or x is greater than strictly mu plus 3 sigma is approximately equal to 0. The area outside this range, just in this little bit here and this little bit here, can be approximately assumed to be 0. Let's take a look at some examples. Our first example tells us that a normal curve has points of inflection with x coordinates 9 and 17. We are asked to find the mean mu and the standard deviation sigma of the normal distribution. Our first step is to write down the general x coordinates of the points of inflection in terms of the mean and standard deviation. We have that the points of inflection, which I write as POI, occur at mu plus sigma and mu minus sigma. Our second step is to form two simultaneous equations from the information given in the question. Since sigma is definitely positive, the mu plus sigma corresponds to the larger version and the mu minus sigma corresponds to the smaller version. Therefore, we have that mu plus sigma is equal to 17 and that mu minus sigma is equal to 9. These are our first and second equations respectively. Our third step is to solve the simultaneous equations to find the mean. If we take our two simultaneous equations and add them up, then what we get is that 2 mu is equal to 17 plus 9, which is 26. Therefore, we have that mu is equal to 13. Our fourth step is to use the mean to find the standard deviation. Since we know that mu plus sigma is equal to 17, it must be the case that sigma is equal to 17 minus mu. And therefore, since we know the value of mu, this is going to be 17 minus 13. That is the value of mu. Therefore, we get that sigma is 4. Our second example tells us that the volume of water, V milliliters, sold in 500 milliliter bottles by a manufacturer is modelled as V is normal with mean 500 and variance 20 squared. A sample of 4 bottles is taken. We are asked to find the probability that all of the bottles contain more than 490 milliliters. Our first step is to find the probability that a particular bottle contains more than 490 milliliters using a calculator. We have that the probability of V being greater than 490 is the same as 1 minus the probability of V being less than or equal to 490. Now again, recall that X is normally distributed with mean 500 and variance 20 squared. So then this becomes 1 minus, and then to work out this probability, bring up our calculator, go into stats mode, and here we have our lower point and our upper point. We need to calculate the probability that V is less than or equal to 490, and therefore we choose as our lower point essentially minus infinity. We have minus 10 to the power of 99. Our upper point is going to be 490, and then we have our distribution, normal, NCD. The correct values of sigma is 20, and the correct value of mu is 500. We execute and we get our value 0.3085. So we have here 0.3085, and upon subtraction we get 0.6915, and this is to 4dp. Our second step is to recall the multiplication law for independent events in the context of the problem. We have that bottle volumes are independent. So therefore, the probability that the 4 bottles are all greater than 490 milliliters by independence is just going to be the probability that V is greater than 490 all to the power of 4. Therefore, for our final step, we are to calculate the required probability. All we need to do is take this number to the power of 4. We're looking for the probability that all 4 bottles are strictly greater than 490 milliliters, and therefore all we need to do is to take our probability of V being strictly greater than 490, which we calculated as 0.6915, and take this to the power of 4, and this gives us 0.2286. Our third example tells us that the masses m grams of red squirrels on Brownsea Island are modelled by a normal distribution, with m being modelled by a normal distribution with mean 450 and variance 50 squared. A naturalist takes a random sample of 10 red squirrels from the population. Find the probability that exactly 2 of the red squirrels have a mass between 440 grams and 460 grams to 3 significant figures. Just a little note, we're going to end up using a binomial probability after this, but first we need to find the probability of a randomly chosen red squirrel having a mass between 440 and 460 grams with help from a calculator. we have that x is normally distributed with mean 450 and variance 50 squared. Now, we're looking for the mass to be precisely between 440 and 460 grams. So again, we're looking for the probability that m is between 440 and 460. Recall that for continuous distributions, it doesn't matter whether you have strict or non-strict, i.e. slack inequalities, because it's the same. Now for this example, it's very easy to use our calculator. Bring up a calculator in stats mode. We have our two ranges, 440 as our endpoint and 460 as our other endpoint. Go on distribution, normal, NCD, and then we have our sigma value as 50 and our mu value as 450. Execute that and we get precisely 0.1585 rounded. This is to 4 dp. Our second step is to define a random variable to help calculate the required probability. We are going to let capital X be the number of red squirrels out of the 10 chosen with masses between 440 grams and 460 grams. Our third step is to choose a suitable model for the new random variable. We have that X is going to be binomial, and we have our index is 10, and we have that our index is 10 and our probability parameter is 0.1585. Again, this is because we're classifying a success in this case to be choosing a red squirrel in this range. And the probability of a randomly chosen red squirrel being in this range is 0.1585. This occurs over the 10 red squirrels chosen from this population. Our fourth step is to recall the formula for the binomial distribution. In the event in general that x is binomial with index n and parameter p, then we have that the probability that x takes a specific value little x is equal to n choose x, and then p to the power of x, 1 minus p to the power of n minus x. Our last step is to calculate the required probability using the formula. We are looking for the probability that x is precisely 2. And therefore, by substituting into our formula, n is 10, x is 2, so we have 10 choose 2, and we have our p-value, which is 0.1585, all to the power of 2, because that's our value of x. And then we have our 1 minus p, which is our 0.8415, all to the power of n minus x, which is 10 minus 2, which is 8. And then working all this out, we get 0.284 to 3 significant figures, or 3 dp. Our final example tells us that the time taken for a train to travel from a town A to a town B is normally distributed with a mean of 1 hour and a variance of 36 minutes squared. Again, this is because the standard deviation is in minutes, but the variance is in minutes squared. The time taken from a random journey from town A to town B is measured. The train is said to be late if the journey took longer than 1 hour and 5 minutes. Given that the journey took less than 1 hour and 10 minutes, what is the probability that the train was late? Our first step is to define the random variable. We are going to let capital X be the time taken in minutes for the train to travel from town A to town B. Our second step is to write down the appropriate distribution for the random variable. We have that capital X is going to be normally distributed with a mean of 60 and a variance of 36, which is 6 squared. Our third step is to recall the conditional probability formula in the context of the situation. We have that the probability that the train is late, given that x is less than 70, this is what we were told, the train is under an hour and 10 minutes, is equal to, using the conditional probability formula, the probability of late and x being less than 70 divided by the probability that x is less than 70. Our fourth step is to calculate the probabilities required for the calculation with help from a calculator. We have that the probability that the train is late and x is less than 70 must mean that capital X is between 65 and 70 by the definition of being late. Now, using our calculator, we can work this out very easily. Again, just as an illustration, we have our 65 and our 70. And to be late, you have to be after 1 hour and 5 minutes by definition, but we know that it's also the case that X is less than 70, so it's in this range in the middle. By using our calculator, we can have our endpoints as 65 and 70. And then we have our distribution, normal, NCD. Our sigma value is 6, and our mean, mu, is 60. We find that this value is 0.1545. Similarly, we need to calculate this conditional probability, also the probability that X is less than 70 in general. Now, this requires slightly more work on the calculator. We now have to have our lower endpoint as being essentially minus infinity, so we have minus 10 to the power of 99. Again, distribution, normal, NCD, all the values are still correct, and so we get 0.9522. Both of these values are to 4 decimal places. Our last step is to calculate the required conditional probability. We have that the probability of being late, given that X is less than 70, is going to be the division of these two numbers. So we have the 0.1545, then we're going to divide by the 0.9522, and therefore we get 0.162 to 3dp.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face, and together, let's make A-level maths a walk in the park.